Another common application of linear programming is in the minimization of feeding cost. The objective is to minimize the total cost devoted to ingredients subject to nutritional requirements. In our objective function, we want to minimize the total cost, which is equals to the cost spent in each ingredient. For each product, the total cost is equal to the unit variable cost times the quantity that we are using of that ingredient. Notice that in linear programming, fixed cost is usually omitted because this type of cost is incurred independently of the choice. Each nutritional requirement follows this general formulation. U represents the quantity of the nutrient present in 1 unit of that ingredient. U1 is the amount of potassium, for example, here, that the ingredient X1 has. In a similar manner, U2 represents the amount of potassium that the second ingredient has. And this must be less or equal than the amount of potassium that is required. In some occasions, you can also have it as greater or equal than. That depends on the specification of the requirement. In addition, we have one special condition. This condition is called the 1 pound condition. In feeding problems, this condition standardizes the requirement to 1 pound or 1 kilogram. In that way, we will know how much of each ingredient is needed to feed 1 pound of the mix to the cow or the cattle. Then we can extrapolate the values by multiplying the value we want to feed. Let's illustrate how we can use linear programming to solve a feeding minimization problem with the following example. Mademoiselle Company produces feedstuff for chicken. According to the nutritional requirements, these are the standards in terms of crude protein, phosphorus, and lysine. The company uses several raw ingredients to produce the feed. The nutritional content of each ingredient is presented in this table. We want to determine what is the minimum cost of the mix given these 4 ingredients. We will formulate this problem as a linear programming problem, and then we will solve it by using our add-in tool solver. Let's start by setting up our objective function. Here our objective is to minimize the total feed cost. Using 4 products: corn, wheat bran, and rice bran. The decision variables are the quantity in kilograms of each of these products. The objective coefficients of each of them are the prices per kilogram. Considering all this information, this is our objective function. In order to establish the structural constraints, we need to use the information given in these two tables. The first one provides the coefficients of the structural constraints, in which each of these numbers are the amount of nutrients presented in each product. The second table provides the right-hand side limits, and these are the upper or lower bounds required of each nutrient. For example, for crude protein, corn provides 78 grams, wheat 114, wheat bran 142, and rice bran 70. And the combination of the four products must be greater than 100, which is the lower limit for crude protein. And in a similar manner, we follow the same criteria for the other two constraints. And finally, we have the 1 pound condition, in which the sum of the four products must be equals to 1. And then we have the non-negative constraints, because the products must be non-negative. As a result, we have the following linear programming problem. Now we need to implement this problem in Solver. Now let's translate our linear programming problem in Excel. First, we need to minimize the total cost. Here in this cell, we will write the objective function. Then we define the decision variables, which are the four products, and the respective objective coefficients. Below these coefficients, we leave in blank the four cells in which Solver will insert the optimal values for each of them. Next, we write the coefficients of the structural constraints in order. Notice, for example, that because corn does not have phosphorus, we leave it in blank. After we write the coefficients, we leave the next right cell in blank. Here we will write a formula that associates each coefficient with the optimal value in order to represent this formula. Then we write the sign and the limit. We have to be careful with the signs, because as you can see here, we will use greater than, lower than, and the equal sign. Now let's proceed to write the objective function. In order to express the objective function, notice that we always have the objective coefficient times the variable. And then we sum all of the expressions. This can be attained by using the formula sum product. We open parentheses and we select the objective coefficients, comma, the optimal values. And we close it and press enter. For the structural constraints, the formulation is pretty similar. We use sum product, we open parentheses, and we select the coefficients of the constraint, comma, and the optimal values. And we close it. Because we will use in each of the constraints the same optimal values for each of the variables, we insert the $sign before the number 7, which is the 7th row in which the optimal values are located. In that way, we can copy and paste the formula. Let's check if the formulation is correct. Pressing F2 allows us to see the formula. And as you can see, for the last constraint, it selected the coefficients of the fourth constraint and the cells that represent the optimal values for the decision variables. Now that we have the formulation implemented, we can use Solver. We select Data and Solver. First, we need to select the cell that represents the objective function, which is D3. Here we want to minimize this objective function. Then we select the 4 cells that represent the optimal values for each of the products. Then we proceed to add each of the constraints. We select the blue cell greater or equal than the constraint, and we add it. And we do the similar procedure for each of the constraints, paying attention that the sign must be correct. And we press OK. We have to be sure that this checkbox is selected, and the method that we will use is simplex. We confirm the constraints are the same as the ones that appear here, and then we press Solve. It says that Solver found a solution. Then we press and select Sensitivity to obtain the sensitivity report. And we press OK. Solver found the following solution. The minimum cost of 1 kilogram of ingredient is $0.21. In order to achieve this minimum cost, we will use wheat bran and rice bran. Among the 3 nutritional requirements, the main critical one is the crude protein because it's the active one. The 1 pound condition is always active because it's an equation. Because this is 1 kilogram of feed mix, in 1 kilogram, wheat bran will represent 42% and rice bran will represent 58%. Looking at the shadow prices, we observe that the only one that has a shadow price between the 3 nutritional requirements is crude protein. Because the sign was greater or equal than, and this is a minimization problem, the shadow price will increase the objective. This means that if we increase by 1 unit, in this case it would be 1 gram of crude protein as a nutritional requirement, this will increase our cost per kilogram by 0.000417 dollars. In summary, this is an illustration how Solver is useful in order to obtain the minimum feed cost.